A specific project I can tell you that we're working on is actually called Sika Copilot, where we are working with an organization called Sikshana Foundation to help teachers in government schools make lesson plans in local language. Like for example, in Kannada, right? We have you may have teachers in a government school wanting to prepare a lesson plan for say algebra, for 8th standard algebra in Kannada. So what Sika Copilot can do is that it can enable a teacher to say, oh, here is how I want my algebra lesson. Here are the concepts I want to teach. I want maybe 10 exercises for the students, and then the LLM can generate that in Kannada.
Hi, wherever you're listening to this, I hope you're doing well. Welcome to Tech Conversations, where we bring you insights from tech entrepreneurs, CXOs, and investors. I'm Hari Arakli, and in this episode, Dr. Sriram K Rajamani, Corporate Vice President and Managing Director of Microsoft Research India Lab, reflects on how computer science and engineering research has evolved at the center in Bengaluru. This lab, which celebrates its 20th anniversary next year, is one of only 3 such international labs for the technology giant, after Cambridge in the UK and Beijing in China. In this conversation, Dr. Sriram also touches upon topics including how AI and large language models can be harnessed to solve local needs, generating lesson plans in local languages, for example, which is an area in which Microsoft India is collaborating with an organization called Sikshana Foundation. Some of the technical aspects of how modern AI models work, and best practices from the research center that could apply to India's deep tech ecosystem. Dr. Sriram, welcome to this conversation with Forbes India, and thank you so much for making time for us. In the industry, of course, you're very well known, and to my layman's understanding, you did some pioneering work in fixing bugs in software in general, among many other things. For a more general audience, we could give us a quick sort of overview of Microsoft Research India as well. I know that you pretty much have spent now, almost close to 30 years, more than 25 years for sure.
This is my 25th year in Microsoft Research and maybe 16th or 17th year in Microsoft Research India.
So just give us a very quick sort of recap and how this center was set up, and we'll go from there.
Okay, thank you, Hari. First of all, thank you for the opportunity. Maybe I'll, since you mentioned, my own background, I'll just say a little bit about my journey and then about Microsoft Research. I'm a computer scientist by training, and my PhD was in this area called formal methods, which is about mathematically analyzing hardware and software systems, right? To find bugs, to make sure that the software and hardware systems we build are of high quality. So that's actually what my own background is in. And the work that you mentioned that me and my colleagues are known for are using these kinds of mathematical techniques, not on just small pieces of code, but on large real world software. In particular, right, we've built software, we've built techniques that find and help resolve bugs in core parts of the operating systems like device drivers, and making concurrent software more robust so that your cloud and your PC and so on run well, right? Those are the kinds of things that I have worked on. About the center itself, I joined Microsoft Research in 1999 in Redmond. This lab was started in 2005, 2006 by Dr. Anandan, and I heard that you interviewed him and Dan Ling at that time, and of course, actually, much has changed. And this lab does work in 4 areas of research. We do work in algorithms and the theoretical foundation of computer science. We do work in machine learning and artificial intelligence, which is such a hot area right now. We also do work in computer systems, which is how to build computer systems themselves, programming languages, verification, kind of stuff that I do. And we also work in an area called technology and empowerment, which is how technology impacts socioeconomic development, inspired by the diverse country we have, that is India. So those are the sort of the 4 areas we work in.
And again, for a broader audience, this center in a way is the youngest outside the US, right? I'm aware of Cambridge in UK and one in Beijing, and this one.
Yeah, this one is one of the more recent ones.
Yeah. And of course, the center itself is now
60,
into its 25th
it's 20th. Yeah, it's I think next year we will have our 20th anniversary.
Okay, 20th anniversary. All right. So can you now talk a bit about over the years, what are some of the research areas that this center has done on? I mean, you just mentioned what you're focusing on today. Just to give us a sense of how research at this center has evolved over the last 20 odd years. And when you started, if you can give us a sense of, at that point, what was the reason, the thinking behind setting up the center? What did you all pick up in terms of your work? And then we can talk more about what you're doing today.
Yeah, I think that's quite a journey. Interestingly, right, we have just refined, moved around, but some of the hypotheses we had even 20 years ago still hold today. So I can also talk about what has not changed and what has changed as well. And so I think one area where we have done very interesting work over many years is our mathematical foundations of computing in algorithms and in hard theory problems. And that's an area we started even when we started the lab, and we still continue to work on this area even today, because India has always had really strong work in theoretical computer science, right? So this center is now known for solving problems that were open for many, many years. One example is actually called the Cadison-Singer conjecture. That's a problem at the intersection of physics actually and computer science that was open for at least 50 years, right? And one of the researchers in our lab, Nikhil Srivastava, solved that problem when he was a researcher here, and now actually he is now a professor at Berkeley. Since then he has moved. So that's an example of a problem that we solved. Another example of a long-standing open problem we solved is actually there's a technique in machine learning called k-means clustering, right? And it's a technique that people use. I mean, everybody in machine learning uses that, but it was not known. The theoretical properties of that algorithm were not known. And Ravi Kannan, who I think was one of our people who established our theory group here, he actually proved mathematical properties of that algorithm, even though that algorithm was there for many decades, right? So that's another. So those are examples of things which are algorithmic hard problems that are open for many decades, that our lab is known for intellectual contributions in solving those kinds of problems. Another area we have worked on is machine learning, and there, one example of a problem that we have been working on is, in machine learning, Hari, as you may know, one very interesting problem is called classification. Classification is that suppose I give you a picture, and machine learning algorithms can classify that picture into a cat or a dog, right? That's an example of what machine learning algorithms can do. In this lab, we started an entire research area called extreme classification. So what is extreme classification? Extreme classification takes objects, could be documents, could be images, could be web pages, could be advertisements, and we classify those objects into one of maybe 1 million categories or 100 million categories, right? You might ask, actually, why would you want to do that, right? It so turns out that there are several situations where that is important, right? One example is, suppose I give you a Wikipedia page, and I ask you, what topic is this page about? The number of topics in the world are very, very large, right? I mean, they are not small like cat or dog, right? Another example is, suppose I give you an advertisement, online advertisement, and I ask you, what are the keyword phrases that are most relevant to this advertisement, so that when a user searches for those keyword phrases, this advertisement becomes somewhat relevant to show. So those problems are called extreme classification problems. And this entire research area was originated in this lab. And today, if you go to a conference like NeurIPS or ICML, which is a top machine learning conference, you will see entire sessions on that topic, or even you might even see a workshop on the topic, right? That actually originated in this lab. Other things that we have worked on are, you may have heard about the whole movement into data privacy regulations, right? You may have heard about GDPR, which is the European regulation for how we manage data, right? There's a project in this lab called Data Map, which pioneered how we take stock of data that is present in our data centers. Right? For a layman, I would just say, actually, think about your house, and do you recall what all you have in your house and where you have it? At least in my house with my kids and so on, I actually don't even. I've lost track of what all I have. Right? The situation in a data center is actually not very different. Like, people store so many things, personal information, private information. So in order to, first of all, adhere to data privacy regulation, you need to first take stock of what data you have. You need to do a data inventory. And then you have to think about policies about, how do we conform to regulations. Like, for example, the European Union has regulations which say that personal data cannot be stored beyond a certain period, 6 months. So we have to first figure out inventory of what all we data have, and then how we comply with those regulations, right? So Data Map was a project that we started in this lab, which was a real pioneering effort in how to even think about how to label data, how to do data inventory, and how to conform to data regulation policies. So that's another thing that we did in this lab. When we were chatting before this interview, you talked about traffic, right? We and IoT and so on. So another project we did in this lab is a project called HAMS, where we used inexpensive cell phones as cameras to we mounted on the windshield, so that actually it can view both the driver and it can view the road in which you are traveling. And then together with video feed from the camera as well as onboard sensors, we can ascertain if the driver is driving safely. For example, we can ascertain if the driver is wearing a seatbelt. Is the driver talking on the phone while driving? Is the driver sleepy? Is the driver tired? Is the acceleration and the deceleration of the car by the driver in accordance with the traffic pattern? Right? I mean, somebody could be driving fast and somebody could be driving safe still, right? But it depends on actually what the traffic is actually around you. So we can ascertain, safe driving practices. We can give a score to a driver, on how they are driving safely, and many, many things like that, right? From those are, some of the examples, and programming languages. We have worked on things where we improve software quality. Another thing we have worked on is in big cloud systems. Efficiency of infrastructure is very, very important. And in this age of AI, there are these things called GPUs, or graphical processing units, which are very expensive resources. And we have done work in this lab on how to optimize and manage those resources efficiently. We have done work on tuberculosis medication adherence, right? How to use technology to help manage the treatment of tuberculosis. So the entire spectrum. And I hope those things sort of give you a spectrum of things that we have worked on.
Yeah. I mean, more recently, since you made a passing reference to AI, it's kind of, even the Aam Aadmi sort of gets the sense of urgency of how much AI is going to change our lives. So can you talk about that? How would you approach researching something like an LLM, evaluating them, and how they affect society at large?
Yeah, so I can cover that. So first of all, machine learning and deep learning is a many decades old field, right? This has been going on for a while. But even for people like us who are in this field, right, these large language models and capabilities of them really came as a surprise. We knew actually that many years down the line, machine learning is going to become more and more powerful. But the progress over the past, say, 4 or 5 years has been breathtaking, even for people like us who are actually experts in the field. This was quite a bit of a surprise. To give you a sense, right, maybe 10 years ago, we could still do deep learning. But we had to build a deep learning system for every problem separately. For example, I talked about classifying a picture into cats or dogs. We could train a deep learning system to first just do that. We could train another deep learning system, for example, to translate Hindi to English, for example, or English to Tamil, for example. But that was a separate system, right? What we didn't anticipate was that so quickly we will be able to build these things called large language models, which are pre-trained. And as one model, they solve many different problems at the same time. That, I think, is the heart of this revolution, right? So previously, right, if you wanted to build a machine learning application, I mean, you could still do it. The techniques were there. You had to hire your own machine learning team and your engineers. You had to collect data to solve that particular problem. And very few people could actually do that, even though it was feasible, right? Because there is shortage of talent. You have to do capital investment. You have to invest in human resources. And then what you finally build solves only one problem, right? And what these large language models are able to do is that they are able to train with all of the data that is present in the internet. And through natural language, they are able to solve many different problems with one model, right? That is the heart of this revolution. And as a consequence, what now happens is that machine learning is now getting democratized, which means that once you have this large language model with you, you don't need a full machine learning team to make this model work for your particular application, right? So in some sense, it lowers the bar for what it takes to make this machine learning work for your particular application, right? And that's really, really revolutionary. And the other interesting part of that is actually you can interact with these things in your own natural language. You don't need a programming language like Python or something like that to interact with this, right? You can just interact with it through your voice or through English text or Tamil text, and the thing responds to it in your own language, right? So that's actually the reason for this revolution, right?
Can you talk about that a bit more? I mean, so the general idea is that much of the internet, it's pretty much English and maybe one or two European languages, but largely English. And these large language models, the really big ones, GPT, whatever, are basically English. And so when you look at a country like India and you want to bring the benefits, I mean, for a moment, bear with me as I ask you about the application side of it. You want to bring the benefits of this kind of work to a small locality which has its own dialect, may not even have a script, and so on. What are some of the science-based methods, processes that you're beginning to understand which work?
Yeah, so there's two aspects to that. First of all, one of the things that is remarkably surprising about large language models is that they are multilingual and multimodal. Even though you are right in the sense that if you look at the content on the internet, which is what these models are trained on, there are, I think, a few languages that dominate the internet. I mean, English is definitely one. Like, if you take German, you take Spanish, Chinese, there are on the order of like 6 or 7 languages, which are high resource languages in the sense that there is a lot of content that is present in them. If you look at, Indian languages, even in Indian languages, right, languages like Hindi, Tamil, Telugu, I mean, they actually have relatively more content, right? But if you look at a language like Gondi or Marathi, for example, right? They don't have actually as much content. So the question that you asked, as to whether these large language models speak all these different languages, the answer varies depending on the language. And in general, right, the more data there is, these models actually speak those languages better. The other thing that is inherent about these models is that they are able to understand languages at a more meta level, in the sense that since they train on all these different languages, right, they're able to transfer their knowledge from one language to a different language. So you don't need to have, for example, an equivalent amount of content in Tamil as you need in English. You just need content above a certain critical mass, and then they are able to converse in their language. So a lot of the work that this lab has done, for example, is first of all understanding what is the minimum level of language-specific data you actually need. How do you collect it? And then how do you even evaluate whether the LLM is actually able to speak in local language, whether it is actually culturally appropriate? So this lab has done, really, really interesting work on adapting LLMs to work in, Indian languages, evaluating actually how they work, and so on. So a specific project I can tell you that we're working on is actually called Sika Copilot, where we are working with an organization called Sikshana Foundation to help teachers in government schools make lesson plans in local language. Like, for example, in Kannada, right? We have, you may have teachers in a government school wanting to prepare a lesson plan for, say, algebra, for 8th standard algebra in Kannada. So what Sika Copilot can do is that it can enable a teacher to say, oh, here is how I want my algebra lesson. Here are the concepts I want to teach. I want maybe 10 exercises for the students. And then the LLM can generate that in Kannada, for example, right? So that is through that experiment, right? We are able to do that because we have a lot of scientific skill to sort of understand what it takes for an LLM to speak Kannada. How much training data do we need? How do we input the textbooks and the curriculum of Karnataka state board to the LLM? How can we ensure that when the LLM generates those things, we have high confidence that the LLM is not hallucinating? How can we actually have confidence on the quality of the content that is generated, right? It is that kind of expertise that this lab has, which enables us to build those applications. And similarly, right, when we build and deploy those applications, that feedback informs our scientific research as well on how people actually use these things.
This is, something that's intrigued me a lot. Again, driving down here, I was thinking about the problems of different languages, and you said that some of these programs can already take less amount of data and begin to generate the kind of useful information that we need.
Yes.
So I'm just wondering, in computer science, do you now already have techniques and technologies where it does not matter which language is kind of being fed into the program, but you've figured out some underlying ways in which you can generate what is useful to us?
Absolutely. In fact, actually, I'm really glad you asked this question. Maybe I'll try and explain to your audience a very deeply technical notion called embeddings. And the reason why I mentioned the word embedding is that the embedding is the internal representation of how these large language models represent something, right? Maybe I'll say it like this, right? If you look at search engines today, right? When search engines got started, they used something called information retrieval, right? So the way we used to build search engines is that, suppose you want to search for Sachin Tendulkar, Mumbai, right? Every document in the world, we used to build something called an inverted index, which is actually what are all the key terms that document has. It's called an inverted index. And so we would build that index for every document. And then what we would do is that we would try and find, and if you want to search for Sachin Tendulkar Mumbai, we would find what are all the documents that contain the phrase Sachin Tendulkar, and that will retrieve a set of documents. Then we would say, which are all the documents that contain the word Mumbai? And then we would actually intersect those documents to find these are the documents that contain both the term Sachin Tendulkar and Mumbai, and maybe that's relevant for this, right? But today, in this era of deep neural networks, right? As an example, right? For example, maybe the term Mumbai is relatively a new term. If you look at old documents, they mention only Bombay, right? If a document contained Bombay, and then you search for Mumbai, those older techniques, right, would not make the connection that Mumbai and Bombay are actually the same thing. They wouldn't know that. But today, actually, these deep neural networks are far more sophisticated. What they do is that they map everything in the world, be it a document, be it a video, be it an audio, into an internal representation called an embedding, right? And you should think about an embedding as a point in a high-dimensional space, right? Like, for example, this point is in this 3-dimensional space, right? These embeddings would be in 400-dimensional spaces, 500-dimensional. So they map everything in the world into a point, right? And the property of these deep neural networks is such that if two things are related, then the embeddings for them are close to each other in the geometric space, right? So as a result, right, Mumbai and Bombay might look at two different terms, but the deep neural network will figure out that the two are the same concept, right? And they will map them to the same point, right? As a result, right, what you can now do is that you can actually ask a question about anything. And your question is first mapped into this dimensional space. And then the deep neural network can look at what are all the surrounding points there and then retrieve those documents. And then actually, those are semantic relationship that these neural networks can do. And since you're talking about that, right? One of the things that we did in this lab is a project called DISC-ANN. And I'll tell you why this is relevant. Is in this era of deep neural networks, right? What you have to now do is that you have to build indices, which are, these big gigantic databases that map concepts to these embeddings so that we can retrieve them back and forth, right? And we have to build these vector indices of trillion scale, which is an enormous scientific and engineering challenge, right? It turns out that one of the projects that we did in this lab called DISC-ANN is such a trillion scale vector index. And there was a NeurIPS paper that researchers from our lab wrote about it, and it is extremely popular, right? Many people in the open source community use it, and many companies now build products based on that. After we released open source, including Microsoft, there was actually Build that was a few weeks ago, and Microsoft has announced products based on ideas for building these vector indices that came out of this lab, as an example.
Yeah, can you talk about that a bit more? I mean, I was sort of tending towards asking you about science that originated at this center, which has found its way into applications in the real world.
Yeah, so that DISC-ANN is definitely an example. The whole point was initially when we started the research project was, can you build these kind of vector indices that are very relevant in this LLM-based world? Can we build them with hundreds of billions of points? Can we build them with trillion points? And can we do that with the performance and with the efficiency that we actually need? And we first started as a research project. Then we published that in conferences. We even actually formed a community called the Big ANN Challenge, in the sense that we gave benchmarks and academics actually competed with each other on what are the best algorithms to solve that challenge. And then it sort of turns out that in order to build many applications, for example, to build copilots, you talked about copilots, right? In order to build copilots, what you have to do is that when you ask a question, you have to first retrieve the documents that are relevant to that question to feed into the LLM. That's a very key part of building a copilot. This technique is called retrieval augmented generation, right? So basically what you have to do is that in order to prevent the LLM from hallucinating, when you ask a question, you need to find which data in the whole internet or in your enterprise is relevant to that question. And then you have to scope those documents and give it to the LLM, and the LLM gives high quality answers, right? It turns out that a system like DISC-ANN is extremely crucial to do that retrieval. So, whatever copilot you build, be it for GitHub Copilot for programming, or any copilot that anybody might want to build, where you want to bring your enterprise data and make it accessible to the LLM, right? A system like DISC-ANN, and people are using it left, right, and center.
Work like this at one level requires some sort of really deep understanding, theoretical computer science and math and all, as you alluded to at the beginning of our conversation, but also requires sort of multidisciplinary domain expertise. So can you give us a sense of how this center is combining that? I mean, deep theoretical knowledge, but also a broader multidisciplinary team. Give us a few examples of your colleagues' work that they're doing. Tell us a bit more about that, the experts that you've assembled under one roof in this center.
Yeah, so a very relevant and very interesting question for this lab. So we have, as I mentioned in the beginning of this interview, right? We have people with expertise in theoretical computer science. We have people with deep expertise in machine learning, with systems, as well as human-computer interaction of how people and computers interact with each other, with a particular bend on low resource, diverse environments that like we find in India. So that's the kind of expertise we have in this lab. We have computer scientists, we have social scientists, we have engineers. That's the kind of community that we have. The way we organize ourselves is through projects, right? So people come up with projects, And a project may have, somebody from a theoretical background, somebody from a machine learning background, somebody from a systems background, somebody from a human. They might all come together to work on, such a project. So, for example, the DiskANN work I mentioned, right? That's a collaboration between a theoretician, a person who knows how to build a large-scale system, and a person who sort of knows how to engineer and make them work for applications. So 3 people started the project, and now many more people have joined. And that's an example of an interdisciplinary collaboration. I talked a little bit about Sika Copilot. Sika Copilot, for example, is an interdisciplinary team that has people that understands how machine learning and LLMs work. It also has people who are social sciences people who sort of understand the realities of a situation in the Karnataka government school and what kind of technology can even be possibly deployed there and how should we deploy them. And then it has engineers, it has systems people, and it has those kinds of people coming together to build such a system like that. I mean, I alluded to HAMS, which is a sort of traffic driver safety system. And even that one, right, has machine learning people, computer vision people, people sort of who understand, how to put things together, people who do field studies on, how the traffic in this country works. So it's sort of those kind of people come together. And I think, what makes the place like this interesting is the fact that, people can come together and work on these kinds of problems with various, expertise.
Oh, overall, you are 50 odd scientists here at the center today. What's the strength of the?
So we are around. I think so I think we would have more than 50 PhD researchers. We also have a team of engineers. We have program managers. So but our PhD count is about what you said is about right. Yeah.
So the reason I asked about that is, and we were talking about just as we were kind of getting into this conversation, you mentioned deep tech, and as you know, in India today there's a lot more awareness and interest in sort of the whole umbrella area of deep tech. And last year the government came out with the deep tech draft policy, how to support deep tech startups in the country and things like that. And some VC firms have also taken interest. From your perspective, how do you look at deep tech? To you, what would you consider as deep tech?
See, if I look at the sort of the history of tech innovation and entrepreneurship in this country, right? We started out by essentially building applications in this country, right? We didn't build things like OS or hardware and so on. The service industry was all about, using our talent and manpower to build the solutions on essentially Western technology. That is how the IT industry in this country got started, right? Then I think the transition that happened was that instead of just building services for companies from the West, we started building startups that serve our own people. Right? If you look at Flipkart or Ola or Meesho, I mean, like many companies, right, which are now building technology-inspired solutions for our large population, right? And even those, if you think about them, right, the origins of the technology actually came from the West, and we sort of customized the business models maybe and sort of tweaked them to make them work for India, right? But I think now, things are very, very different right now. If you look at the innovations that are actually possible, something like DiskANN. DiskANN is a technology that originated in this lab that actually many people around the world are using. And there are examples of that are coming not only from this lab, from various parts of the country, right? Where we are not just becoming consumers of technology that was designed in the West. We are making originators of technology that originates in this country, and it's actually applicable throughout the world. So that's actually a shift that is actually happening in India. And I think that's actually possible because the quality of the expertise in this country has actually gone up. Indigenous science, indigenous technology development in this country has now reached a capability where we, I think, are able to now be producers of technology. And that's a really interesting situation we are in as a country. Yeah.
To your mind, can you think about whether this ecosystem can evolve into something that can generate real science-based products? So I'm just wondering where you see us on that journey, where a lab in IISc or a lab in CCamp can come up with something from lab to commercialization. Where do you think we are at?
Yeah. So, one can look at that question at multiple levels, right? Now, one thing actually I have seen happen from the time I came here is that if you look at scientific publications in these deep tech areas, over time, I have seen papers written out of India being studied at Stanford and MIT. You could go to courses like in Stanford and MIT, and there'll be papers out of this lab or out of IISc. They are actually studied, and they are part of the syllabi of top universities in the US. I think we have in this lab initially, right? We used to say, oh, look at this, this paper that my colleague wrote is now part of a course at Carnegie Mellon, and we used to get a kick out of that. And at some point, we even stopped counting, right? Because that has actually happened. Now it has become more routine, right? We are, in that sense, actually, we are part of the idea generation machine globally, right? I think Indian computing and Indian science is already there, right? Now, the next step is actually whether those, basic ideas get built into artifacts, right? Which could either become products, of companies in India or elsewhere. I think we see bits and pieces of that happening as well. Maybe in not the same volumes as you would see in the UK or in the US, but there are certainly instances of that happening even in the tech industry, particularly I think in things like biotech. I think there's probably even more of that actually happening out of India. The other thing that I think is very unique about India is the fact that in order to build anything that works in this country, right, you have to actually build it at very low cost. You have to build it in such a way that it works even when there are so much failures in the system and so on. And I see that also actually giving a unique tilt to the science that comes out of this country. The science that comes out of this country typically is actually always built so that actually you can build something at very low cost and so on. And those become applicable actually elsewhere in the world as well. And I think I can imagine, even recall work from the lab actually, which has, that kind of flavor. But that said, actually, I would say, Hari, what I find that there are very high quality deep tech people in this country for sure, much more than, how many I would count, when I returned to India in 2006 compared to that, right, there's much more. But I think the volume is not comparable to the size of our country. That's what I would say, right? We really need more quantity and more quality in order to achieve the kind of aspirations that you outlined. But I think we are on a path. We just need more people who are capable of doing deep tech. That said, actually, the number of people now are much more than what they were 3 years ago or 5 years ago. But I think for the size that our country has, right, the amount of talented people we need is a lot more. So one of the things we do as a lab is that we teach at PhD. A lot of my colleagues actually teach at IISc. We co-supervise PhD students, throughout the country. A lot of us are affiliate appointments with, universities. So we consider that as an integral part of, our community, being as part of our community in India.
While you were telling me about this, I was thinking about how, as a sort of an organization with the mandate to do deep science research, but also being part of a sort of corporate organization, you are one of the biggest industrial research organizations. What might be, some of the learnings one can take away or best practices that might come to your mind, which we can learn from, because we now really need to encourage deep science collaboration from lab to commercialization. What do you think has worked for you within the research organization to come up with really high quality work?
Yeah, so I think there are a few things that we have learned as an organization, which we can share with the community. The first one is actually making sure that you hire extremely high quality people, right? I think, and we have taken time to do that, right? And that's, I think, very, very important. The second thing is giving them the time and space to work on hard problems, right? Some of these things I mentioned, like the Caddison-Singer conjecture, for example, or this KNN or extreme classification, they took many, many years of research to actually do them. And in the initial stages, right, if I look at those projects, right, when they were first proposed, it was not even clear whether they will succeed, how they will succeed, whether the algorithms and the approaches that were proposed by the team, will it even work? They were like unknown. So one of the things that we have learned as a lab is to trust a small group of peers who have a passion to go after something with the confidence that we trust their expertise, because we have hired them, because we have high quality people, and we let them drive the research agenda rather than me as a manager trying to influence what they do. We trust their instincts. So that's the second thing that we have learned. The third thing I think we have learned is actually when they do that, you create an environment where they constantly get peer feedback from within the lab, from within other Microsoft research locations throughout the world, and from the community at large. And you do that by publishing, by engaging with the external community and getting peer feedback, right? Because in every area, the experts in that area are the ones that have to talk, not management, right? So you also create a feedback cycle where the feedback comes from the best experts in that area throughout the world, and you create that feedback loop, right? And then the fourth thing you do is that you encourage our scientists not only to write papers, but to build their ideas into systems, deploy them in the real world, and see whether they actually work or not, right? And you create that feedback loop too, right? And when you do those, right, it just so turns out that you create an energy where people choose their battles, get a bunch of peers together to get mind share around those battles, and become scientists and technologists who push the state of the art and solve real world problems. So I think those are some of the learnings that we have had. So I think I would say that for the community, be it IASC, be it startups, right, I would say the number one thing we need is patience. We need high quality people, and we need patience so that we don't look for what we can just build in 3 months and 6 months. And if you do that, right, you will only skim the surface. Like the kind of things you said, you'll probably build something that you can build in 3 months. It will not be very deep. Right? So we have to give ourselves the grace of time.